Hey everyone, welcome back to my channel. Today, we are diving deep into the fascinating story of how our magnificent sun came into existence. Get ready to embark on a cosmic journey through time and space. The journey begins billions of years ago, amidst a vast cloud of gas and dust known as a nebula. Within this swirling cosmic soup, gravity began to play its role, pulling together the scattered particles and initiating the formation of a newborn star. As the dense core grew hotter and denser, a nuclear fusion reaction ignited, unleashing a tremendous amount of energy. And so, our sun burst forth, radiating light and heat that would eventually shape the destiny of our solar system. Join me as we unravel the intricate chain of events that led to the creation of our celestial giant, and discover how it continues to sustain life on our planet even today. But before we get started, make sure you hit that subscribe button and turn on the notification bell, so you never miss any of our mind-blowing videos. By subscribing to our channel, you will not only stay updated with all the amazing content we offer, but you will also become part of our growing community of passionate viewers. We believe in creating a platform where knowledge and entertainment go hand in hand, and your support enables us to continue delivering top-notch videos that inform, inspire, and entertain our audience. So go ahead and hit that subscribe button, and let the learning and fun begin. Alright, let's jump right in and explore the exciting topics that await us in this video. The birth of a star. Billions of years ago, in a vast cloud of gas and dust known as a nebula, the first chapter of our solar system's story began. Gravity acted as our cosmic storyteller, pulling the matter together, and as the pressure increased, the temperature rose exponentially. This intense heat allowed the atoms within the nebula to collide with greater force, sparking a series of nuclear reactions. The process of nuclear fusion commenced, as hydrogen atoms fused together to form helium. This fusion reaction released a tremendous amount of energy, causing the young star at the heart of the nebula to ignite and shine brightly. As the star grew brighter, its gravitational pull on the surrounding matter intensified, leading to the formation of a rotating disk called a protoplanetary disk. This disk became the birthplace of countless smaller celestial bodies, including asteroids, comets, and planets. Within this chaotic environment, tiny particles began to collide and stick together, gradually forming larger and larger objects. Over millions of years, the force of gravity shaped these objects into the planets, moons, and other bodies that make up our solar system today. It is within this magnificent tapestry of cosmic events that the story of our solar system truly took shape. Finally, when the temperature reached a staggering 15 million degrees Celsius, nuclear fusion ignited. This marked the birth of our sun, releasing an unimaginable amount of energy and light. The process of nuclear fusion, which occurs within the core of the sun, involves the fusion of hydrogen atoms to form helium. This reaction releases an enormous amount of energy in the form of light and heat, which is what we perceive as sunlight. It is this continuous release of energy that sustains the sun and allows it to shine brightly in the vast expanse of space. This fusion process generates an incredible amount of heat and pressure, with the core of the sun reaching temperatures as high as 27 million degrees Fahrenheit. These extreme conditions cause the hydrogen atoms to collide with such force that their nuclei fuse together, unleashing tremendous amounts of energy. It is this ongoing process of nuclear fusion that powers our sun, providing the energy necessary to sustain life on Earth and influence the dynamics of our solar system. The birth of the sun, with its intense light and energy, is truly a remarkable event in the vast cosmos, shaping the destiny of our planet for billions of years to come. The sun's structure. Now that we know how the sun came into existence, let's take a closer look at its structure. Our giant ball of fire consists of three main layers: the core, the radiative zone, and the convective zone. The core, located at the center of the sun, is where nuclear fusion occurs, generating an immense amount of energy through the conversion of hydrogen into helium. This energy is what ultimately powers our star and provides heat and light to the solar system. Surrounding the core is the radiative zone, a thick layer where energy is transported primarily through the radiation of photons. Within the radiative zone, these photons bounce off the particles, gradually making their way towards the outer layers. Beyond the radiative zone lies the convective zone, a region characterized by the movement of plasma and heat through convection. Here, energy is transferred through the motion of hot plasma rising and cooler plasma sinking, forming giant convection cells that can be seen on the sun's surface as solar granulation. Understanding the structure of the sun allows us to comprehend the fascinating processes that occur within our closest star, shaping the dynamics of the solar system as we know it. The intense pressure and temperature at the core of the Sun create the ideal conditions for nuclear fusion to take place. Within this powerhouse, hydrogen atoms collide with such force that their nuclei combine, forming helium atoms. This fusion process unleashes a tremendous amount of energy in the form of light and heat. In fact, the energy released from each fusion reaction is equivalent to millions of billion megatons of TNT. This continuous release of energy is what sustains the Sun's immense brightness and heat, providing the necessary conditions for life to thrive on Earth. Without the fusion reactions occurring at the core, the Sun would not be able to maintain its stability and radiate the energy needed to support life in our solar system. Surrounding the core is the radiative zone, where energy is transported by photons. It's a dense region, taking thousands of years for photons to traverse this vast space. As the photons travel through the radiative zone, they undergo a complex journey. Often compared to a crowded highway during peak hour traffic, the photons constantly collide with atomic nuclei, scattering in all directions. These collisions cause the photons to change direction and energy, making their path through the radiative zone far from straightforward. This constant bouncing around, known as random walks, is what causes the long time it takes for the photons to reach the surface of the Sun. So, despite traveling at the incredible speed of light, these photons face a labyrinthine obstacle course before they can escape the Sun's gravitational pull and continue their journey towards Earth. Finally, we have the convective zone, where energy travels through convection. Hot plasma rises, cools down, and sinks back down in a continuous cycle. This acts as a bubbling cauldron, ensuring the energy generated by the core is distributed to the Sun's surface. The convective zone plays a crucial role in maintaining the Sun's equilibrium. As the hot plasma rises towards the surface, it carries a tremendous amount of energy from the core. This energy is in the form of radiation and is transferred to the surrounding plasma. As the plasma cools down, it becomes denser and sinks back down, creating a continuous cycle of energy circulation. Without this convective motion, the energy generated in the core would remain trapped and the Sun would not be able to sustain its intense luminosity. The convective zone can be thought of as the Sun's natural heat pump, ensuring that the energy from the core is effectively transported to the outer layers, allowing the Sun to shine brightly. The Sun's magnetic powerhouse. Aside from its remarkable structure, the Sun is also known for its mesmerizing magnetic activity. The Sun's magnetic field plays a crucial role in shaping the dynamic and awe-inspiring phenomena that occur on its surface. Solar flares, for instance, are explosive events that release massive amounts of energy, causing a sudden burst of light and heat. These magnificent eruptions are often accompanied by the ejection of charged particles into space, known as coronal mass ejections. Sunspots, on the other hand, are dark regions that appear on the Sun's surface and are caused by intense magnetic activity. These spots can vary in size and shape, with some being large enough to fit several Earths inside them. Lastly, the Sun's magnetic interactions with our planet's magnetic field create the spectacular phenomenon of auroras. These dazzling displays of colorful lights occur when charged particles from the Sun collide with molecules in Earth's atmosphere, creating a dancing spectacle that lights up the night sky. In summary, the Sun's mesmerizing magnetic activity is truly a sight to behold and continues to captivate astronomers and enthusiasts alike. These magnetic processes are a result of the Sun's rotation, which causes loops and twists in its magnetic field lines. Sometimes, the magnetic field becomes extremely tangled, leading to explosive releases of energy in the form of solar flares. These solar flares, often referred to as nature's fireworks, occur when the twisted magnetic field lines suddenly reorganize and release a tremendous amount of energy into space. These powerful eruptions can propel a torrent of charged particles called solar winds out into the solar system. As these charged particles interact with the Earth's magnetic field, they can cause geomagnetic storms that may disrupt satellite communications, power grids, and even pose risks to astronauts in space. Scientists study solar flares and their associated phenomena to better understand and predict their impact on our technological infrastructure as well as space exploration missions. By unraveling the mysteries of these explosive magnetic events, researchers strive to minimize the potential harmful effects on our modern society while harnessing the Sun's energy for various applications. The importance of the Sun. Now that we've delved into the origin and structure of a Sun, let's talk about its significance to life on Earth. The Sun's role as the ultimate source of energy cannot be overstated. Every beam of sunlight that reaches our planet carries heat and light, warming our atmosphere and illuminating the world around us. This vital source of warmth not only determines our climate but also allows for the existence of liquid water, which is essential for the survival of countless organisms. Moreover, the sun's energy is harnessed through photosynthesis, a process by which plants and algae convert sunlight into chemical energy. This process not only sustains plant life but also forms the foundation of the food chain, providing nutrients for herbivores and eventually carnivores. In essence, the sun's immense energy serves as the life force that sustains the intricate web of ecosystems on Earth, making it a vital component in the cycle of life. But the sun's influence reaches even further. Its gravitational pull is responsible for keeping our solar system intact, determining the orbits and motions of all the planets, moons, and asteroids. This immense force of gravity not only governs the movements of celestial objects within the solar system but also has significant effects on space and the activities of satellites and spacecraft. The gravitational pull of the sun can alter the trajectories of these artificial objects, requiring careful calculations and adjustments to ensure their stable functioning and safe navigation through space. Additionally, the sun's gravity plays a pivotal role in shaping the structure and dynamics of the entire Milky Way galaxy. As the sun moves through the galaxy, its gravitational field interacts with neighboring stars, affecting their positions and movements. This complex interplay of gravitational forces forms the foundation for the intricate dance of celestial bodies in the universe, illustrating the profound impact the sun has on the cosmic stage. The future of the sun. So what does the future hold for our beloved sun? As incredible as it may seem, the sun is an ever-changing celestial object. Over the course of billions of years, it will exhaust its hydrogen fuel and begin to expand, becoming a red giant. This expansion will occur because the sun's core will shrink, causing the outer layers to increase in size. As a result, the sun's surface temperature will lower, and it will emit more energy. Its immense size will swallow up nearby planets, including our very own Earth. Although this seems daunting, it is still billions of years away, and scientists believe that humanity will have found new homes among the stars by then. The transformation of the sun into a red giant will mark the beginning of the end for our star, but it will also serve as a reminder of its grandeur and the cycles of the universe. Eventually, it will shed its outer layers and transform into a white dwarf, glowing with a faint, ethereal light. This marks the end of the sun's life cycle, but fear not, as this process will take billions of years. So, no need to worry just yet. The transformation from a main sequence star, like our sun, into a white dwarf is a fascinating celestial event that occurs as a result of a star's internal processes. As the sun exhausts its nuclear fuel, it will start to expand into a red giant, engulfing the inner planets in its fiery embrace. However, once the nuclear reactions in its core cease, the outer layers will begin to drift away into space, leaving behind a dense core called a white dwarf. This small but incredibly dense object will still emit a faint glow, radiating the remaining energy it has stored over its long existence. With its outer layers stripped away, the sun's white dwarf phase will mark the peaceful conclusion of its stellar journey, a reminiscence of the once vibrant and powerful star that illuminated our solar system for billions of years.